Today, we want to start connecting things up and rather than learning lots of new things, learning about how the different forms of system descriptions that we have, frequency responses and transfer functions, how they're related, and also getting poles and zeros in on that as well. And most particularly, where we want to end up is having an appreciation for how the locations of poles and zeros affect the design of the system and particularly the frequency response that a system has, and how we can actually manipulate the poles and zero positions in order to achieve certain shapes in our magnitude response when we're designing digital filters. So first, we want to connect up h of z, the transfer function, with the frequency response, h of f. Then we'll revisit finding steady state responses using the transfer function as opposed to the frequency response. And then make that connection between how do pole and zero locations affect the frequency response, the shape, particularly of the magnitude response, but then also the phase response of the system. And as part of that, we'll introduce a new graphical method for connecting those two. And then ultimately leading to the requirements of pole zero locations that we need to achieve different digital filter design specifications. So finally getting to the place where we have enough analytical knowledge, enough understanding of the interrelationship of these different descriptions in order to start not just analyzing systems, but designing them. And we'll introduce our first actually legitimate design technique for discrete time filters, namely one where we design the shape of the magnitude response by the locations of the poles and zeros. So moving finally from analysis to design. But first, let's look at the applications that we can do with our current knowledge of the Z-transform. And one that we found the DTFT was quite adept at was finding steady state responses. If I put in a discrete time signal that was a cosine or sine of some particular frequency, F0, maybe with some phase and some magnitude, we knew that if we had the frequency response available, all we had to do was evaluate that frequency response at the particular frequency we were putting in. That would give us the magnitude and phase contribution the system would make to that signal. And all we had to do is scale the amplitude of our cosine by the magnitude of h of f at that frequency and add to the phase whatever the phase angle of h of f was at that frequency. We didn't need to use convolution. We didn't need to do either in the time domain or the frequency domain. And so we wouldn't need even inverse transforms to do this problem. We could do it that way, but that would actually be the harder way to do it. We had this shortcut method of using the definition of the frequency response to help us figure out how a signal like this would be affected by the system. We'd like to do that again, but we don't have the frequency response exactly available to us. We have, if we did, we know we just take that original signal. When it goes out through the system, it comes back with the same form. The systems can't change its shape. It's still a cosine or sine. It can't change its frequency as long as it doesn't alias. And so it retains the scaling of its own magnitude and the phase shift that it came in with. But the system will add to that. We'll affect it by changing its magnitude, by scaling it by the magnitude of h of f at the particular frequency we put in on, and shifting it by whatever the phase was when we evaluated h of f, the complex frequency response at the particular frequency. But if we don't have h of f value available to us, we have the transfer function h of z. What do? Well, then we're going to take advantage of the relationship between the h of z transfer function and the frequency response h of f that came out of the way we defined the z transform originally. So we have, if we're given this problem, we have basically three different methods that we could apply. If we wanted to apply discrete time Fourier transforms, then we know we could get h of f either by transforming the difference equation or transforming the unit sample response, and then evaluating it at the particular frequency we put in. Now with z transforms, we can find h of z by the same sources, either z transforming h of n or z transforming the difference equation and rearranging it. But now I need this way to relate the z's in h of z to the frequencies f and h of f And there is a relationship, the same one that we derived when we came over from the DTFT to the Z-transform, and we'll revisit that. Today, we'll also show you a graphical method for connecting those two transforms. So let's do this by example. We'll take our simple single feedback IIR filter, y of n minus 1/2 y of n minus 1 equals x of n. And we'll put a sinusoid into this, a discrete time sinusoid into this system, a 3 sine pi n plus pi over 6. And I want to know, for that signal, what's the steady state response? What's coming out? Now, notice this isn't a sine with a u of n after it or anything like that. It's one that we turned on a long time ago, and we're continuing to drive with this sinusoidal waveform. So the steady state response we're getting is like a forced response of the system to this particular input. If we were going to approach this by using the DTFT frequency response, we know first we need to find out what frequency this discrete time sinusoid is. And if we set the frequency argument 2 pi nf equal to what we have in our sinusoid, pi n must be 2 pi nf. Solving for f, we get f equals 1/2, which is actually the Nyquist rate. So we're putting in a Nyquist frequency signal, and we want to know what's going to come out of this particular system. Well, we can find the transfer function very quickly by Z-transforming the difference equation, and we've done this one in the past. So we know, just repeating that here quickly, that it happens to be 1 over 1 minus 1/2 z to the minus 1, or z over z minus 1/2. Now, if we want to convert that h of z to the transfer function to the frequency response h of f, we can recall the relationship, the similarity between the Z-transform of h of n and the DTFT of h of n, that using their summation definitions, they actually do look identical. In fact, they are identical if we choose a particular set of values for z. If we let z be e to the plus j 2 pi capital F, then, and if we only allow z to be those values, then that quantity raised to the minus n power gives us the same term that's in the DTFT definition. And so if I have a transfer function or a Z-transform, and I want to go to its equivalent discrete time Fourier transform, I can simply make this substitution. Replace z with e to the plus j 2 pi f, and I'll be left with a expression that is the frequency response, the discrete time Fourier transform version of that quantity. So we could take our h of z that we just derived, replace z with e to the j 2 pi f, and be right back to our discrete time Fourier transform frequency response, which in this case is 1 over 1 minus 1/2 e to the minus j 2 pi f. Now we simply do this the same way we did back in DTFT days, because that's what we're working with. We plug in f, our actual f equals 1/2, into the frequency response and evaluate that expression. It turns out that we plug in f equals 1/2 into 1 minus 1/2 e to the minus j 2 pi f is 1/2, leaves us a 1 minus 1/2 e to the minus j pi. So that's at an angle of minus pi. That's around on the negative real axis at a distance of 1. So that's a minus 1 instead of that exponential. Or if you prefer, e to the minus j pi is cosine pi, or cosine minus pi, minus j sine pi, which is minus 1. Evaluating this, we get 2/3, a real value, so it has, and it's positive, so its angle in the context of a complex variable is 0. And so our steady state response would be the original 3 sine pi n plus pi over 6, scaled by 2/3 and shifted by no additional phase. And that would be our steady state response. Now, when we make this substitution, when we change z into e to the j 2 pi f, what we're doing is putting it at a distance of 1. E to the j, anything has a magnitude of 1. And in the terms of the z-plane, we'll be located at all values of z that have a distance from the origin of 1, and that is, in fact, the unit circle. If we're setting z equal e to the j 2 pi f, that means the angle of the point that we're dealing with on the unit circle is given by 2 pi f. And so we can relate frequency, discrete time frequency, with z location in the z-plane on the unit circle. For example, for f equals 0, we have e to the j 0, which is 1. The frequency response location for f equals 0 or dc is looking at what's happening at z equals plus 1. Likewise, if we move around here, set z equal to plus j, that's at e to the j pi over 2. If we ask what frequency is that, we set pi over 2 equal to 2 pi f and find that that frequency is 1/4. Likewise, z equals minus 1 is like e to the j pi, and we set pi equal to 2 pi f and find out that f is a half. And down here at minus j, we're at f equals either plus 3/4 or minus 1/4 if you're coming back the other way. So we can relate locations on the unit circle, their angular position, with frequency, and find out what z value is given by that frequency. And instead of finding the frequency response h of f, we can actually plug these z values directly into h of z to find the same answer. Now, for our particular problem, we had a frequency of 1/2. That was what's going on over here. So if I want to know how does the system behave when I put in a signal with a frequency 1/2, I can evaluate my transfer function, h of z, at this z value, z equals minus 1. So if we approach the problem that way, we have z equals e to the j 2 pi f0. Plugging in f0 as a half, that's e to the j pi, that's where we were. That's a z value of minus 1. We plug in for h of z, we put z equals minus 1 in there, and we get, it shouldn't be minus 1 in the numerator, it should be 1, or I guess it's this one, minus 1 over minus 1 minus 1/2, which gives me a 1 over 1.5, or 2/3 again. Same answer. And so we can again take, just as we do with the frequency response, take these complex values, scale the signal by the 2/3, shift it by the 0, and have the steady state response of the system. So we can start with either h of f or h of z. If we have h of z, we can either jump to h of f or just figure out what z position are we at by relating the angle on the unit circle to f0, get that complex value for z, plug it into h of z, and we'll get the complex frequency response value for the frequency that we evaluated. The other way to think about this is that analogy we brought in last time, that rubber sheet analogy. If we think about how the magnitude of the transfer function is affected by pole zero locations, we know that if we take a rubber sheet, and if our system has equal numbers of poles and zeros, we'll stretch that out at a height of 1, and then tack down any place there's a 0 at those z locations. We'll tack down the rubber sheet, and above any position where there's poles, we'll push it off to infinity, and then let the sheet make whatever surface contour it can to connect in between those. And we get some shape like this for this particular example, where I have 2 poles here on the real axis and 2 zeros at plus or minus j. You see the rubber sheet tied to 1 at infinity because we have 2 zeros and 2 poles. So h of f as or h of z as z goes to infinity tends towards 1. Above the poles were pushed up to infinity, down exactly at the zeros were tacked down to the z-plane at the height of 0. And the rubber sheet, if you will, takes its shapes from there. Now, that's what's going on for h of z, the transfer function, at least the magnitude of the transfer function. How does that relate to the frequency response? Well, we said the frequency response is given by just the values of z that have a magnitude of 1 that are sitting on the unit circle. And so as we go around the unit circle, we're effectively operating at different frequencies, different digital frequencies, starting out here along the real axis at z equals +1. That's like DC. Right? And as I walk around the unit circle, if we want to know what's the magnitude of the frequency response doing, well, that just relates to the height of the rubber sheet above that position, that Z position. So DC, we go up and see where we intersect the rubber sheet. And at that point, that happens to be a height of 4 here. That's the same as the magnitude of the frequency response at F equals 0, because we're at an angle of 0 here. Now, on my rubber sheet, you see this black line. That's the projection that I've created of what points are on that rubber sheet directly above the unit circle. So it's the projection of the unit circle on the rubber sheet. And we'll see as we walk around the unit circle here, we're advancing up higher and higher in frequency till we get around to the backside here. We said that's f equals 1/2, and then come back around to f equals 1. And in terms of what the frequency response of the system looks like, well, it's going to be this projection of the unit circle, or what is above the unit circle of my rubber sheet as I move around the unit circle as I increase frequency. So as I start walking around the unit circle, the height of the rubber sheet traces out the shape of the magnitude response of the system. And so this shape, this contour shape, straightened out, unfolded, is the same as the magnitude response of the system that we see. So see that again, starting at frequency 0, we're starting over here at z equals 0. To get up to the Nyquist rate, we're following the unit circle around to the z equals -1. And the height of the rubber sheet as we walk along there and look up, that's the same height that we'll have for this contour of the magnitude response of the system as we increase frequencies. And if instead of the magnitude of h versus z, we plotted the phase of h versus z, we would be tracing out this phase plot. And so here's the pole zero diagram for the filter we were trying to solve our little problem for, our steady state response problem for. It was y of n minus 1/2 y of n minus 1 equals x of n, has this h of z that has 1, 0 at z equals 0, has a pole at z equals plus 1/2. And so we see the contour of the rubber sheet there tacked down to well, pulled down to 0 at the origin, pushed up by this pole around here in the positive real axis, giving us this little bump, and held off at a height of 1 at the wings. And so what we see as we move around the unit circle and look up at DC, we see the highest peak in the magnitude response. As we move around behind here, we see the rubber sheet getting pulled down lower and lower. The point is that it's the pole and 0 locations that are pulling and pushing on that rubber sheet. And what it's doing above the unit circle is what translates into the shape of the magnitude response of the system. So as you can surmise, if we want bumps in our magnitude response, if we want to push it up, we're going to need some poles nearby. If we want to push it down to give some attenuation, we're going to need some zeros nearby. Well, we'll go into a little bit more sophisticated way of looking at it than that, but that's kind of the idea. Now, there's another way to look at this, another way to graphically understand how the pole and zero locations affect the shape of the frequency response of the system. In fact, both the magnitude and the phase response. And that's what we call the graphical interpretation of frequency response, or the graphical method. The argument for it goes like this. Here's a transfer function for your system. It's got some zeros, got some poles, might have some gain k. We find a transfer function and then we factor it. Factor it so we can find the zeros and the poles. And then perhaps we plot a pole zero diagram. All right. What we're looking for is a way to relate this to the frequency response of the system. And so we wanted to know what's the magnitude and phase of this transfer function, and what is it as we move around the unit circle where the frequency response lives. Well, in general, h of z is a complex function. It's usually a ratio of two complex polynomials. And so if we have the magnitude of a complex ratio, if we're looking for that, we know that's the magnitude of the numerator divided by the magnitude of the denominator. And the magnitude of the numerator, because it's a product of a bunch of terms, if they're complex, the magnitude of the product is the product of the magnitudes. So we would put magnitude signs around all these individual zero terms, and likewise the pole terms. And if we want to know what's happening at some particular frequency f0, we're looking for the frequency response at this particular frequency, we know we have to go up on the unit circle. We have to evaluate h of z at z equals e to the plus j 2 pi f0. So we figure out what that angle is and find that position on the unit circle. If I evaluate this analytical function I have for h of z, and I want to know what the magnitude is, I'm going to plug in z0 into my h of z and then find the magnitude. And so everywhere there's a z, we'll replace it with a z0. And if we had all these numeric values, we could simply compute it if we like. For our purposes today, though, there's something to recognize, and that is that each of these individual magnitude terms in the numerator and denominator represent vector distances on the pole zero diagram. Specifically, this magnitude of z0 minus z1, that's the vector distance between z1 and z0, where z0 is the point on the unit circle we want to operate, and z1 is the location of the first zero of the system. And if I have more zeros, I would just have more vectors from all of them to this same point. And we're going to divide that by the distances from all the poles. And this z0 minus p1 is the distance from z0 to p1, the length of this vector that I'm calling vp1. This quantity then that gives me the magnitude response of the system at this z position, which is the magnitude of the frequency response at frequency f0, is given by, well, k, if there's a multiplier out in front, times the product of all the vector distances from all of the zeros we have to the point we're operating at, divided by the product from all of the vectors from all the poles to that same point. In this case, I only have one, but I could have multiple ones. And those products of distances multiplied by k will actually give me the correct numeric value for the magnitude of the frequency response at frequency f0, or the magnitude of the transfer function h of z at z0. Similarly, if I have a complex ratio like this, and I want to know what's the phase angle of that total result, Well, it would be the angle of the numerator minus the angle of the denominator. If I have a ratio of two complex values, I subtract their angles. And each of these, the angle of the numerator, well, I have a product of potentially complex values. If I have products, I add their phase angles to get the total phase of the product. And so the angle of the numerator is the angle of the vector that goes from z0 to z1 plus the angle that goes of the vector to z2, the angle to vector to z3, however many vectors I have from zeros to that operating point, I'll add up all their individual angles. And I'll subtract off the sum of the angles from all the poles. So again, I'll draw vectors from all the poles to that point, add up all their angles measured from the horizontal, and then subtract the sum of the pole angles from the sum of the zero angles and get the total phase of the system at this operating point. So in our one pole, one zero case we have here, to find the angle of h of z at z0, which is the same as finding the angle of h of f at f0, I would take this phase angle, the theta of z1, the zero phase angle, and subtract phi p1, the angle from the pole, and that would be the phase angle of h of z at z0. So I can use the vector lengths to find the magnitude. I can use the vector angles to find the phase. Okay, let's do that with a couple of poles and zeros because it's a little clearer if we have more than just one. Here I have a case, same operating point, z0, but now I have two zeros and two poles. We're going to draw vectors from all of those to that point of operation, which represents operating the system at frequency f0 or determining the transfer function at z equals z0. The magnitude of h at that z0 position is going to be any gain factor we have, k, times the product of the distances from all the zeros. So this vector z1, that length, multiplied by the vector from z2 to that point, those two vectors, I'd multiply them together, scale them by k, and divide them by the product of the vector from p1, this vector, and that length from this vector p2, these two lengths multiplied together would be in my denominator. In terms of the phase angle, I'm going to add the zeros, the angles from all the zeros. That would be this angle theta z1 added to theta z2, again measured from the horizontal. And I'll subtract off the sum of the angles from the poles. There should be a plus sign in there, which would be phi p1 added to phi p2. Sum of the angles from the zeros minus the sum of the angles from the poles. And that would give me the exact magnitude and phase of h of z at z0 or h of f at f0. This method is also useful not just to get numeric values, but to also give us a sense, if we keep this ratio in mind, as we move around the unit circle and get further away from or closer to different poles and zeros, it gives us an idea for what the shape of the magnitude response of the system is going to be, or the phase response of the system will be, based on these vector distances and angles. Let's do a numeric example to make it a little bit more clear, a little more understandable. There's too many symbols floating around there. So let's simplify this. Let's get a 1, 0, 2 pole system. I have a 0 at c equals plus 1. I have two poles that are in complex conjugate positions at plus or minus j 1/2. And I have an overall gain k of 2. So we know what our zeros are. We know what our poles are. And we want to know, for example, what is the magnitude and phase of the frequency response at f0 equals a quarter. Well, first off, we got to find where we are operating on the unit circle. So we go to e to the j 2 pi times a quarter, which is e to the j pi over 2, which is up here at plus j. The magnitude response of the system at this frequency then is our k, which is 2 in this case, multiplied by, let's draw our vectors in. In the numerator, we have the vector from z1 to that operating position. In terms of a distance, it's over 1, up 1, so its total vector length is square root of 2. We're going to divide that by the product of the distances from the two poles to that point. This pole is at j 1/2, so this has a length of 1/2. This one is at minus j 1/2, so it has a length of 1.5. And again, we know k equals 2. And so we get our total response, the magnitude response at that particular point from these poles and zeros. In terms of what the phase angle is at this frequency, we'll take the angle from the 0, that's this one here, and that's 45 degrees above the negative real axis, so it's at 90 plus 45 this way, 135 degrees. And we're going to subtract off the sum of the distances from the sum of the angles from the two poles. Both of them are sitting at 90 degrees though. So we'll have 135 minus 180, which is 45 degrees. And so that's the response of the system at this frequency is this magnitude and this phase. So if we were to use the graphical method for our particular problem, then I need to get the pole zero diagram for my h of z here and evaluate it at f equals 1/2. So our system has a 0 at z equals 0 and a pole at z equals plus 1/2. And I want to know what's going on at, we said f equals 1/2. That's over here on the unit circle at e to the j 2 pi times 1/2. So it's e to the j pi. We're over here. We have no k value. There's no gain here, so k equals 1. I only have two vector distances. The vector from the numerator from the 0 is a length of 1. And the denominator, we have a length of 1.5. And so we get our 2/3 again, just as we did analytically. And my total phase angle is the angle from this 0 back over here, which is at pi. And actually, pi is also the angle from both of the poles as well, or from the single pole, I'm sorry. And so we get a angle of 0 in total. So we got the same response values from this graphical method that we got by plugging in f into h of f, plugging in z equals -1 into h of z. So again, this method, this graphical method, can give us numerical answers like this. It can also give us a sense for what the shape of the magnitude response of the system is going to be. Again, if I think about what's happening as I walk around the unit circle and draw vectors from this pole and this 0, we see that, well, over here at f equals 0 or z equals 1, I am as close as possible to this pole here. So my denominator term is going to be as small as it's ever going to be. So that's going to be my peak magnitude point. As I move around here, notice the distance from the 0 never changes. It's always 1. So my numerator is always 1. The denominator is the distance from this pole. And as I move further and further around, that's getting bigger and bigger and bigger, making the denominator bigger of this ratio. So we see that as frequency increases, my magnitude response should be decreasing, which is what we saw in the other in the other graphs of the response. So this method can give us a qualitative idea of what the shape of the magnitude response of the system is if we think about the length of those vectors. Okay, and that's what we want to do now. We want to connect pole zero locations and how they affect frequency response. And understanding that, we can either think about that rubber sheet analogy or think about the vector lengths and angles in the graphical method. Either of those two should give us a qualitative idea for what the shape of the magnitude response, or the phase response for that matter, is going to look like. And the idea is we want to gain some insight into how pole zero locations affect the shape of the frequency response of the system, so that we could actually design some digital filters based on moving around poles and zeros in the Z domain into the Z plane, which is a legitimate design method. It's known as a filter design by pole zero placement. And let's think about what the implications of some of these things we've seen with the graphical method and the rubber sheet have to say. First of all, since frequency response is what happens as we walk around the unit circle and plug in those Z values, any poles or zeros that are near the unit circle are going to have the most dramatic effect on the shape of the frequency response. Like if we have zeros right on the unit circle, if you think about the rubber sheet, that's going to bring down the rubber sheet exactly to zero at that point. And so zeros on the unit circle will for sure guarantee we get magnitude responses of zeros. As we walk around the unit circle, the rubber sheet's getting pulled up quite a bit. And as we get close to this pole, it's really pulled up hard nearby. And so we're going to be seeing some peaking, some gain in our system as we get close to poles. And again, as we get near other zeros that are near or on the unit circle, we're going to be pulling down the magnitude response. And if the zero is right on the unit circle at that frequency that it's sitting on, we have to get a magnitude response of 0. So zeros on the unit circle cause complete elimination of signals, complete filtering, complete removal, and pull down the response nearby, pulling down that rubber sheet. If we think of the graphical method, that's so because we have a 0 distance in the numerator. The distance from that 0 to that operating point at z equals -1 is 0. And so the magnitude has to be 0. And as we go around, get close to it, get closer and closer and closer to it, this numerator term is getting smaller and smaller and smaller and smaller, pulling us down. All right, we can see that with our rubber sheet analogy as well. When we have the rubber sheet, a 0 here on the unit circle, that rubber sheet's pulled all the way down to 0, so we absolutely have to get the magnitude response that's pulled down. This pole in the middle is holding up the rubber sheet, pushing things up. And as we see, the combination of pushing things up in the middle and yanking them down over here is letting them rise up a bit on the other side. And that's giving rise to our low-pass filter kind of shape. One way to make a low-pass filter is push up the middle and pull down the high-frequency area here. This happens to be exactly the response of a two-point averager, y of n equals 1/2 x of n plus 1/2 x of n minus 1. If I double up things, if I put 2 zeros on here and 2 poles here, I just exaggerate the effects a bit. In this case, because my zero's over here on the low frequency side, I create a low frequency dip. In this case, pull it all the way down to 0. And don't pull down the high frequencies, I create a high pass filter. Another common use of zeros on the unit circle are things like comb filters. This is a filter that's designed to get rid of some frequency and all of its harmonics. So we have a 0 amplitude response point at some frequency and integer multiples of it. We create those by putting zeros right on the unit circle and equally spacing them so that we get the right frequency spacing to get all the harmonics of that original signal. If we put a bunch of poles, an equal number of poles in the center, then that holds everything up. And if I have the same number of poles as I have zeros, h of z tends towards 1 as z goes to infinity. That also holds up the edges. And then these little zeros just create notches down, pull down, drag down the rubber sheet at these points. Poles on the unit circle, on the other hand, aren't allowed. They create instability, right? In terms of our graphical method, if we think about that, putting a pole on the unit circle means at some frequency, I'm going to have a 0 in the denominator, which is going to make it run off to infinity. So placing poles right on the unit circle is bad news. We're going to get frequency responses that want to head off to infinity as we come around here because the rubber sheet's pushed up to infinity there as well. So not a good plan. We don't want to do that. And that's commensurate with when we looked at transfer functions and the requirements for stability. All of our poles had to be inside the unit circle for causal systems. If we put poles near the unit circle, that's okay, as long as they're inside if it's causal. That just pushes things up, pushes up the magnitude response. As we get closer and closer and closer to those poles, some term in the denominator is getting smaller and smaller and smaller, making the ratio get bigger and bigger and bigger. So having a pole getting in the proximity of the unit circle means, again, we're going to be pushing up the rubber sheet with the pole nearby, giving us a little bit of gain there. If we want to create something like a bandpass filter, if we want to accentuate a certain range of frequencies, we can push those poles out a little bit further. If it's not at DC or at the Nyquist or at f equals a quarter, if it's some other value, we're going to need 2 poles. We're going to need complex conjugates to do that. We'll see why in a moment. But what's happening is as we come around the unit circle, as we come around at higher and higher frequencies, we're getting closer and closer to this pole. We're coming around looking at the projection, then we're getting closer and closer to where the rubber sheet's getting pushed up. And we're kind of riding a little roller coaster here as we go by the pole. In terms of the graphical method, my vector distance from my 0 is not changing. The numerator is not changing, but the vector distance from the pole is getting smaller and smaller and smaller in the denominator, which again, causing the ratio to go up. And the closer I move the poles to the unit circle, the more drastic the peaking is, the more we're pulling up the rubber sheet, the shorter the vectors are in the denominator. We get taller and narrower peaks when that happens. Now, if you put a pole or a 0 at the origin, as we saw in that last example, it has no effect on the shape of the magnitude response of the system. It's always the same distance away from every point on the unit circle, right? So if I have either a pole or a 0 at the origin, no matter where I am on the unit circle, that vector distance is not changing. It's always 1. Doesn't matter where I am. Now, in this case, I won't get a flat magnitude response because the vector distance from the 0 is going to be changing. It's going to go from 0 to getting bigger and bigger and bigger. So I have a high pass filter here. Turns out an FIR filter, a non-recursive filter, must have all of its poles at z equals 0. If I violate that, the difference equation I recover from my pole 0 diagram will have to have necessarily some y of n minus something terms in them. Here's the transfer function for an FIR non-recursive filter. And when we convert it to our standard factorable form for poles and zeros, we get rid of the negative exponents by multiplying through by powers of z. We'll have some zeros that come from these terms, but in terms of the poles, they all have to be at the origin at z equals 0. If I happen to have a pole and zero at exactly the same location, they effectively cancel each other out. It's like removing common factors from the numerator and denominator of h of z. So having a pole and a 0 at z equals 1/2, well, here I have a pole. If I drop a 0 on it, it's like it's not there. Just as we would cancel out those two terms as common factors in the ratio h of z. Now, that's actually a design method if you have an undesirable pole in your system somewhere. You can design a 0 to sit on top of it and eliminate it. It's actually more reliably done in discrete time systems if the origin of that pole happens to be something in a discrete time design, not in some analog component. So we have these design rules that we can apply that kind of dictate where we want to put poles and zeros to create either FIR or IIR filters or low pass or high pass. In general, we're going to want stable causal systems as well. So we can look at the design rules around that. For a causal system, we need the number of zeros in the h of z to be less than or equal to the number of poles. In terms of our h of z, that means the order of the z polynomial in the numerator of h of z has to be less than the order of the polynomial in z in the denominator of h of z. If we violate that, like in this example, I've got a second order numerator and a first order denominator. So I have 2 zeros, 1 pole. If we divide these back down to make negative exponents in trying to convert this to a difference equation, we cross multiply h of z as y of z over x of z. So we cross multiply and get these terms. And we inverse ZTransform. We get a y of n minus 1 term, a y of n minus 2 term, an x of n minus 1, x of n minus 2. Now, typically, I don't want to write a difference equation in terms of y of n minus 1, but y of n. So let's advance everything by one step. And I have a difference equation y of n plus 1/2 y of n minus 1 equals, x of n plus 1. That's a non-causal system. And that will happen anytime I have more zeros than I have poles. If I want my system to be stable as well as causal, we said all the poles have to be inside the unit circle. And we saw that with our transfer function as well. If we had a causal or right-sided system, the region of convergence cannot include any poles. And if we want our region of convergence to include the unit circle, all those poles would have to be inside the unit circle, because for a right-sided system, the region of convergence starts at some radius and goes outward. Now, I alluded to this before, but it is also a design rule that if I want my difference equation to have real valued coefficients, like y of n equals 2x of n minus 3x of n minus 1, if I want those ak and bk coefficients not to have any j's in them, then if I have a complex polar zero, I have to have its complex conjugate as well, so that the imaginary parts will cancel each other out when we can recombine them to get the coefficients of the difference equation. So if I have one complex zero or pole, I have to have its conjugate being the same position, just with a negative j, the opposite j value, or the opposite angle, a negative angle. Like if I had zeros at plus or minus j, those are complex. I have both conjugates, so that's fine. When I recombine them, the imaginary parts will cancel each other out and leave me just real valued coefficients, which lead to a real value difference equation. So I can have complex conjugates. Or can have complex values. I just have to have them as in conjugate pairs. Now things get interesting when we start designing linear phase filters. Turns out I can only make linear phase filters out of FIR filters. And so the first requirement is to make an FIR filter, all the poles have to be at z equals 0. It also turns out that if I have a 0 on the real axis at some radius r from the origin, to have a linear phase, my filter also has to have another 0 at the reciprocal radius at 1 over r away from the origin. And if I happen to have a complex 0, I have to have its complex conjugate, and each of those must also have other zeros at the same angles and at, again, reciprocal radii. So if this one's at r e to the j theta, I need one at 1 over r e to the j theta. And because I have conjugates, I need also one over r e to the minus j theta to go with this one. If I have that, then I will have a system that actually has a linear phase curve. The exception to that is if I have a 0 on the unit circle, radius 1 is its own reciprocal, so it doesn't need to have anything else added to it. Here's an extreme example of one. I have 3 zeros, or 4 zeros, 2 of them on the unit circle, and one here on the real axis at z equals 0.284. To get a linear phase response, the straight line phase curve, I need another 0 out here at 1 over 0.284, which happens to be 3.522. Quickly, if I want a minimum phase system, meaning I want the phase angles of the phase response to be as small as possible, which is sometimes a desirable thing, I can't have any zeros outside the unit circle. Because when I do that, as I trace along the unit circle, the angles that I get are always really big because they're measured from the horizontal. So I don't want to do that. I need zeros inside the unit circle to minimize the angles. And finally, if I want a filter that has a very high Q, a lot of peaking or a very narrow passband for a notch filter, if I want to make a notch filter, and we'll do this in a couple days, I can put a 0 right on the unit circle to completely eliminate that frequency. If I wanted to have a narrow notch, I can move poles out along the same radius at the same angle and get closer and closer to that 0. The closer I get to it, the sharper my transitions are. Let's see a picture. Here's a notch filter. I've chosen the frequency of 0.2 that I want to get rid of. I put a 0 on the unit circle at the right angle to notch out that frequency, and I get that. And I put a pole behind it at a radius of 0.6, and I get a kind of this wide notch. If I move that pole much, much, much closer on the same radius to the 0, then I still get the same notch frequency. That's set by the 0 position. But now notice the width of that notch got much narrower. And so we can actually control the width of notches or bandpass if we don't have the zeros there by the proximity of the pole to the unit circle. We're out of time, so we'll stop at that point. We will come back and try to do a design example with that. Have a couple more topics on ZTransforms to finish up. 2 big ones coming up. We need to finally address how to do inverse ZTransforms. We want to put to use some of these design ideas to see how they are implemented. And that'll take us through the next week or so. We do have an exam coming up, so please make sure you're catching up with the material.